Welcome everybody to our Gamma seminar. Today we have the pleasure to guest Marcin Krych, who is going to talk about the application of the k-contact geometry in dissipative field equations, about recent paper we sent to the archive. Indeed, it appeared today. So please, Marcin, the floor is yours. Go ahead. Thank you.
Okay, thank you. So yes, as I was introduced, I will talk about applications of k-contact geometry in dissipative field equations. So let me go to the outline. I will start my talk by talking about the fundamentals of k-contact geometry. Then I will present some theorems that allows us to better construct the k-contact structures for some PDEs. And then I will go to applications. So starting from the basics, I have to define what is a k-vector field. So it is basically a section of a vector bundle as written here. My cursor is visible or not? I'm sorry if I can ask.
Yes, and the typos too, because this should be M, yeah, instead of Q.
Yes, I'm sorry, because sometimes it was clear. Okay, right, sorry. It should be M here, yes. It should be M here. So yes, the k-vector field is a section of such a vector bundle, such that the following diagram commutes. And from this diagram, we also see that k-vector fields are basically represented by a family of vector fields on M. We also have to define what is a first prolongation. Basically, if we have a map from some open set on Rk to the manifold, then we can lift it to a map from an open set to the direct sum of the tangents to the manifold. And it is lifted in the following way, as it is written here. Yes, we just use the tangent maps and use the canonical vector fields on Rk. So if we know what is a first prolongation, we may now define the integral sections. These are basically maps from U to M, such that they satisfy the following formula. It works in a similar way as integral curves for normal vector fields. However, of course, we have to introduce the integrability of k-vector fields, because it is not guaranteed that every point on the manifold is in an image of some integral section. And if one wants to check if the k-vector field is integrable, then there is a pretty easy condition. One only has to check if the vector fields with which the k-vector field is constructed are commute.
Marcin, to make this clear, you can say that yes, the integral section is a solution of this system of differential equations, and that this system of differential equations is a PDE, a system of PDEs, where the partials in terms of the independent variables of phi are described like the values of the k-vector field on the point of the manifold, the image of the section. As the natural analog of the first order differential equation of the integral solution or integral section of time dependent vector field. You can write this in coordinates. It's more clear what it means. Yeah?
It's more clear. Okay, I should have written this. Okay, right. Okay, makes sense.
Intrinsically, it's cool. It's nice, but to see what is going on, if you write it in coordinates, it's very.
Okay. Okay, so now I go Yes, so now I go to the k-contact structure. A k-contact form on an open set of a manifold is a differential one form on U, taking values in Rk, such that the kernel of the differential form is a regular non-zero distribution of current k, and the direct sum of kernel of eta and kernel of differential of eta is equal to the tangent of U. I haven't written this a regular distribution, but it was a regular distribution is a smooth distribution and a distribution of constant which has constant rank. And smooth distribution is such that it is locally spanned by vector fields. Okay, so if we know what is a contact form, we can now define a co-oriented contact manifold. So basically, if we have a k-contact form defined on a manifold M, then the pair, the manifold and the k-contact form is called a co-oriented k-contact manifold. And the kernel of the differential of eta is called the Weyl distribution. If additionally the manifold has the dimension as stated here, and if there exists an integrable distribution with the rank nk, then the triple is called a polarized co-oriented k-contact manifold. And the distribution is referred as a polarization of the k-contact manifold.
By the way, yes, may I have a comment about?
Yes.
Yes, and Narciso, if you think otherwise, you invented these things with Xavi, so tell me. But as much as I know, this is because you have a Darboux theorem. You wanted a Darboux theorem for k-contact structures, and the canonical example is the first jet, yeah, essentially, well, the dual version of the first jet. And so in that case, you have n independent variables, k-dependent variables, and nk partial variables, yeah? So that's why it's the dimension n plus k plus nk. And that's why the distribution you have here has rank nk, because it's the natural polarization. It's the vertical distribution of the partials on the derivatives of the coordinates, dependent on independent. So
yes,
this is... This looks
I
like...
just wanted to say that later I will tell about Darboux coordinates, and they are
Okay. Okay, I understand. Yeah.
For polarized.
Right.
Yes.
So please go on.
Okay. So yes, but I still also have to say about the vector fields. It is a uniquely defined family of vector fields induced from the k-contact manifold. These are basically vector fields that satisfy this. And as I said, they are uniquely defined. And they form a basis of the kernel of differential of eta. Yes, so an example of a canonical k-contact structure. Okay, that example is that manifold here. It has a canonical contact structure. It may be defined as it is defined as written here, where theta is a Liouville one form defined for Liouville one form which is canonical for cotangent bundles. It is also a polarized co-oriented k-contact manifold because the polarization can be constructed as a vertical distribution of the bundle as written here. Of course, we have the canonical coordinates. They are provided by the canonical coordinates on the cotangent bundle and the canonical coordinates here, so we get something like this. And for all of this, the eta and the distribution look like this. And basically, we also have this. These are basically called the Darboux coordinates. And for every polarized co-oriented contact manifold, they exist around every point. And yes, these are the coordinates such that eta looks like this, kernel looks like this, and the distribution looks like this. I also have to tell about the contactification. It basically means that if we have a k-symplectic manifold, which satisfies this, which has for which exists a one form, it is called an exact k-symplectic manifold. Yes, exact k-symplectic manifold. Then we can construct the k-contact structure by. Yes.
Could you explain what is a k-symplectic structure for those who don't know?
Okay, a k-symplectic structure is basically a manifold with a K2 form. It is the two forms has to be closed, and I don't remember if more.
And what it has to satisfy? Because you have introduced something and you said nothing about it.
Yes,
many of
I
us we
assume
know,
that
but
we
not
know
everyone.
it. I mean, it is technically more basic, but yes.
Because a k-symplectic structure is just a family of k
yes, it is a
forms that are closed and
yes,
whose common kernel is 0. Okay, this is a k-symplectic structure.
Okay. Yes, okay.
Yeah. Okay, and when you have this and you do the differential, it's like doing the differential of every coordinate. So omega in this case has
yes. I also
two forms, and theta, the one you wrote, also has k coordinates that they are force, differential one force. Yeah, when you do the differential, you do it on the coordinate.
Yes,
yeah?
I didn't really explain this notation, but yes, it is.
Next
we use
time, try
one
to
bolded
write it
to.
simple. Yeah. Okay.
Yes. Okay.
Let's go on.
Okay. So go on. So okay. Yes. So we have the contactification. We are constructing a contact structure by taking the one form and just. I mean, here we just constructed the one form and we construct manifold in this way, and we have a contact structure. Okay, so now we can go to the Hamiltonian systems. So if we have a k-contact manifold and we define some Hamiltonian on the manifold, we can define the following equations. The solutions of these equations are called eta Hamiltonian k-vector fields, and the triple is called the eta Hamiltonian system. In Darboux coordinates, it looks like this. And it should be noted that for k greater than 1, the solutions are not unique. The equations can be also written for the yes, the equations can be also written for the integral sections. Then they look like this, and if we write the integral section in Darboux coordinates, we have a system of equations that look like this. And it is important to note that both equations for k-vector fields and for integral sections, they are not fully equivalent because k-vector fields may not be integrable. So it is possible to have solutions which are k-vector fields, but don't have integral sections as a solution. Yes. So now we want to say something about the regularity. So if we have a Hamiltonian k-contact manifold, we say that it is regular if the fiber derivative, which on coordinates looks like this, is a local diffeomorphism. And if the fiber derivative is a global diffeomorphism, then it is hyperregular. And of course, if H is regular, then it is equivalent to the fact that the Hessian matrix is non-singular at every point. And it also means, what is probably the most important, that from these relations, we can find the momenta as a smooth functions of these things. Okay, and now pretty important theorem. So if we have a Hamiltonian, a pretty concrete Hamiltonian that is also regular, and we take some integral section of some k-vector field, then the integral section projects onto a map that satisfies a second order system of partial differential equations. Yes, more precisely, if this denotes the local inverse of the fiber derivative, yes, then the functions satisfy the second order system of partial differential equations of the form like this. Yes, okay. And further, if we assume that dimension of this manifold is equal to 1, then we can actually say pretty much, because yes, because then if we can check the matrix A, and if it's definite, then the resulting second order equations are elliptic, so S is elliptic. If it has a signature k-1, 1 or 1 k-1, then we obtain a hyperbolic equation. And if A is indefinite with at least 2 positive and 2 negative eigenvalues, then the equation is of the ultra hyperbolic type. Okay, like
if you allow me, yes, Marcin. I mean, what you said is true, but the nice thing is to explain more or less the idea of this. And the idea is that you want to describe physical system PDEs by means of k-contact structure. So there are several manners to do so. One of the manners is to describe these PDEs as a system that comes from a k-contact Hamiltonian system on a canonical model with a certain Hamiltonian. Yeah, this is what you are doing in here. So you have a certain Hamiltonian in this canonical model, yeah, and with a canonical structure eta that you have given before. So when you write this, what you can do is that for the Hamilton de Donder Weyl equations, that it's called these equations for the sections of the K Hamiltonian you have, yeah. The fun thing is that you can construct a PDE, a system of PDEs of second order that is going to describe certain physical systems. So what you are going to do in this thing is to relate the properties of the k-contact model with the properties of the PDE you want to start. Yeah. So this is one model of doing this. This is one thing. Another thing that you haven't commented, I don't know if you would be afterwards, is that your Hamiltonian may be polynomial in the Z alpha. This normally we call them dissipative variables because they are used to describe dissipation. And in the literature, most of the Hamiltonians, they are affine. What we did is just to make some sense of this polynomial relation to describe new physical systems and to describe them, in particular systems that they are non-autonomous. Yeah, that you know, this is something that maybe will appear in example. But this is the main idea of this stuff. You want to describe system of PDEs by means of k-contact Hamiltonian systems, and you are going to describe several canonical models, and you are going to describe how the properties of these canonical models, they are going to describe the system of PDEs. And this is a general model that works for many examples. This is the main idea, okay? To say what we want to do, okay?
Yes,
okay,
yes,
please
yes,
go on.
because yes, I really didn't talk about the main idea because later also in the applications, the task is to have some partial differential equations with some physical sense, and to find the Hamiltonian, I mean the k-contact structure basically with
Yeah,
Hamiltonian. Yes,
yeah,
so
sure.
it was the main idea, and the theorems here, together with this, it helps in doing it. We will, of course, later encode some partial differential equations in the canonical k-contact manifolds.
And also, it's nice to say that regularity is necessary, because otherwise you will not be able to construct the system of PD. Yeah, this is the thing that allows you to describe it in terms of the partial of the configuration variables, the Q, E, in terms of the independent variables, the alpha. If you don't have the regularity, you have no manner to describe the momenta in terms of the velocities of the paths of the derivatives. So you cannot. This technical condition is necessary. Okay, please go on.
Okay. So now I will talk about the contactification of an exact k-symplectic manifold. Okay, I mean, if we have some exact k-symplectic manifold, and we have we have the k-contactification of it, then a section satisfies the k-contact Hamiltonian, the Donder Weyl equations. There should be big H, but yes. If and only if they satisfy these equations, I think these equations are nice, because for some good Hamiltonians, they basically split the phi, which is the element of pi, which is the field on pi, and they split the dissipative quantities. So I think there was a corollary in which it is visible that we can seek a solution such that, I mean, if we want to model some partial differential equation for phi, for some Hamiltonians, we can just have fixed, I mean, we can find some fixed dissipative values that always hold this, and we can just focus on this equation. If I understood the idea, I think yes.
Yes, I mean, the first partial differential equation you have there, it will be written, it will be a first, by means of certain regularity conditions, it will be a second order differential equations for certain variables, yeah? And the dissipative part, it will be essentially determined by means of the second partial differential equation. You will split, you will have a part concerning, yes, the dissipation of the second half, yeah? And you will have something that will be a solution of the first PDE. This is the main idea of this.
Yes.
Please go on.
Okay. So now I will talk about the adapted exact two-symplectic structure. It will be a bit different construction, but it will be very useful, because I think the half of the applications is using it. So if we have a okay, we have canonical projection with some manifold n, and then the n-dimensional manifold. We have some Liouville one form on the cotangent bundle, and we have some basic one form. Basic, it means that is the pullback to the cotangent bundle of a differential on n. And then the cotangent bundle is endowed with the adapted exact two-symplectic structure if we define the k-symplectic, yes, if we define the k-symplectic two form in such a way. And of course, we have the associated two contactification, which is defined by taking that manifold and taking that one form. The important, okay, like, why is it interesting? It is interesting because in most of the applications where we will use it, we'll also use some extra coordinates, and the basic one form will often pair the extra coordinates with the coordinates that are actually interesting. Yeah, so we will see it in the examples better. And of course, we will like to use it for the partial differential equations. So we also have to say something about the regularity. We will define the P regularity. So if we define M in the following way, and it is a two-contactification of an adapted exact two-symplectic manifold, and we have a Hamiltonian, we say that H is a P regular if the partial fiber derivative given on coordinates in the following way is a local diffeomorphism, and similarly, if it is a global diffeomorphism, then it is hyperregular. And also, well, we have the equivalent conditions. If H is pi regular, then the Hessian matrix is non-singular at every point. And also, what is the most important, the pi can be solved. They are the SMAF function. They can be represented as a SMAF functions of y, v, and z. Okay, so now if we have the manifold and we have the two contactification of an adapted exact two-symplectic manifold and the Hamiltonian, which is pi regular, then every solution that we present in this way, yes, every solution of the Hamilton, the Donder Weyl equation satisfies locally a second-order system of partial differential equations for the variables y. And more precisely, it is a local inverse of the relations like this. Yes, and then it satisfies something like this. And also we have a condition for the dissipative variables. Okay, and I think we can now go for to the examples. So, for example, we have a damped Klein-Gordon equation. It is described by the partial differential equation that looks like this. And we will do it simply using a canonical two-contact structure and using the Darboux coordinates. I mean, we can guess the Hamiltonian, and one can calculate that it gives such a system of partial differential equations.
Marcin, just one thing. There is one thing important in this PDE, and the PDE is that you have written this ZT on the PDE. And the thing you have to say that is important is that this can be considered to be any function of the time and of the position. Okay, it's any function.
Okay.
It will be any function. And okay, so it's something about a PDE that it is non-autonomous, that has some dependence in the coefficients on the dependent variables. Yeah. So
okay.
And the fun thing is that the Hamiltonian that you have down, you have written, is quadratic, on terms of the ZT. You haven't said it, but normally the Z alpha are called dissipative variables. So it's quadratic in a dissipative variable, and this is going to be a key to describe by means of key-contact geometry of this PDE that is non-autonomous. It is something that normally doesn't happen for key-contact structures because they were thought rather for autonomous dissipative systems. Then Xavi and Narciso invented something more general than key-contact for dealing with this, but you can do it without it. And this is one of the nice things of the method. Oh, okay, you can go on.
So now we can talk about Allen-Kahn type equation. That is a partial differential equation that looks like this. And for this one, we are yes, we are constructing an adapted exact contactified two-symplectic structure. Yes. So we take P0 equal to R4. We take the coordinates and we define the the differential form. We say that this one is the canonical one and this one is the basic one. Yes, and we obtain the exact two-symplectic. We can obtain the exact two-symplectic manifold in this way, and we can contactify it.
Marcin,
Yes.
better to explain it a little bit more because, okay, you have the theta, yeah, you have a 2, 1, 4, yeah, because it has 2, 1, 4s, yeah. One of them is the typical Liouville one, yeah, the PXTU X.
Yes, that's
QX.
next to E2 is a typical Liouville one.
Yeah, and this has the role of defining some coordinates, configuration coordinates, U, B, U, and B, and defining several momenta, P, X, Q, X. Now, the differential of that is a symplectic form because it's the canonical one on a cotangent bundle. So
Yes.
whatever you add to that, any other symplectic, any other two form you will add to that, it will be always a two-symplectic because the kernel of one of them is equal to 0. So no matter what you will write as a first coordinate of the theta, okay, this, the differential is going to give you a two-symplectic manifold, an exact two-symplectic manifold. Now, the first part, the UDU, UDV you have on the left, yeah, this is one for that depend only on the coordinates, on the configuration coordinates U, U, and B.
Yes, this is the meaning of the basic.
Yeah, only is a basic form. Why? Because here you have two things. One is the Liouville form that allows you to define the momenta, the configuration variables, and then you have a second one form, yeah, that is only on configuration values. And when you will get the contactification, the two contactification, the first component of the theta, yeah, the one that it is a base one, will mix the variables U, U, and V in such a manner that you will get a nice system of PDEs to be solved. This is the main idea. The fault that this theta has, yes, is quite easy because one is a Liouville form and the second one is something that depends on the configuration. Is something that allows you to define PDEs. Second, it will be allow you to define second order PDEs, provided the Hamiltonian is regular, and the definition of regularity is the typical with a cotangent bundle, because here you have a cotangent bundle, you have U, Px, B, and Qx. So by means of the regularity and this form, you will be able to split the Hamilton, the Donder Weyl equations that you will get. And this is why this works. And this is why this is very general and very useful to get examples. Okay, this is because you can't explain it, but the main thing is that it's easy because the way of writing it is very, very simple. Yeah. And you have to take into account why is this money, why it works. Okay.
Okay.
Go on.
Okay. Okay, yes, maybe I will add that, yes, because U is the coordinate that is interesting for us, and V is an additional coordinate. And I didn't write the differential equations that we get from this Hamiltonian, because with this Hamiltonian, but it's actually will be something like, we'll get this plus an equation for V, but that equation for V will not be interesting because it will not get any additional constraints, and V is not interesting for us because it's an additional. Yes, it's an additional coordinate.
Marcin, that is true, but yes, for another occasion. One of the problems with all this formalism, the k-contact to describe PDEs, is that it's difficult to find a Hamiltonian or to find a method to describe the PDEs properly. So much of the things we have in here, this way of constructing or writing the equations you didn't write, was to find a manner to guess the Hamiltonian or to write the equations properly. Okay, this is one of the main things, because when you have k-contact, geometry, as much as I know because of Xavi, he said to me is that it is difficult. So this method works quite well to find the Hamiltonians and gives you many possibilities. Okay, please go on.
Okay. So now we are going to the next example. Okay, so now we'll consider a partial differential equation of this form. Yes, we restrict for ourselves to U greater than 0. And we'll consider a two-contactification. I mean, it will be similar method as before. We are taking R4, which will be isomorphic to the cotangent bundle of R2, so something like this. And I mean, it is very similar to the previous one. We also define the k-contact one form, which looks like this. For this, we can of course calculate the k-symplectic two form. And yes, and we are able to do a contactification, which leads us to a k-contact one form. Yes, it was Liouville one form, I think. Yes, it leads us to k-contact one form. And for this Hamiltonian, it can be guessed that Hamiltonian may look like this. Okay, so the next one, it will be a complex Linzburg-Landau equation. Of course, we can split it into two equations by just writing the imaginary part and the real part. We have two equations. We can define something like this. I mean, it is the similar method as before, but more coordinates. We define A, B, C, D with momentas, and we also define the one form in this way, where this one is the this one is the Liouville and this one is the basic form. Yes, of course, we can calculate the k-symplectic form, and we can do a contactification that allows us to calculate the k-contact form, one form. And this Hamiltonian is the yes, and we can guess that Hamiltonian may look like this, and this is Hamiltonian that recreates the partial differential equation. Okay, now damped nonlinear Schrödinger equation in real form. So now we have equation like this. Yet again, we can split it into two equations. Similarly, we have the coordinates. We can define the one form where this one is a Liouville one form and this one is a basic. We can take the k-symplectic, then the contactification, and find the Hamiltonian that looks like this, and it also works. Okay, now Fisher KPP equation with linear loss, so it looks like this. And yet again, we have the coordinates, we have the basic and the Liouville form. We have the k-symplectic structure, we have the k-contact structure, and for this, we can guess the Hamiltonian like this. Now a damped quadratic field on a Minkowski space. We have the equation which looks like this. Okay, and for now we are using the canonical for contact manifold with the canonical coordinates and canonical k-contact form. And we can find the Hamiltonian that looks like this, and it works.
You know, Marcin, yes.
I mean,
Next time, as I said, one of the important things is why this works, how to do it, yeah. And the best way to do it is instead of saying one example after another, is to write one of them in full, or three, or even three if you want, four of them in full, and just to explain why it works. Yeah.
Yeah. So we should. I should
next time. Yeah.
Yes, I should have written every one because they are really similar, to be fair. But yes.
Yeah, but you know, you haven't explained many of the things. That's what I told you that
Okay.
much better to say. Can you show me the previous one, the previous example?
This one?
I mean, yeah, just 2 comments, you know, because you know, you have the first differential equation. It's that first differential equation PDE that depends on you. Yeah. So the thing is, if you try to describe it as this exactly as a model that depends only on you, is very difficult. That anyone that has tried to do this, I think that knows that you have to add something.
Okay.
So the trick is that you add another configuration variable, B.
Yes.
Yeah. Then you construct the momenta, the cotangent space, yeah, to R2 where the variables are UV. So you have the UV form now. Now, you have to add to the theta the other one form, yeah, the second one, the extra one. So how you do it? You do it in such a manner that writing the combination that is proper in terms of the configuration variables, the V and the U, after writing the final equations, the Hamilton, the Donder, Weyl, the way of these equations allow you very easily to split the equations into 2 equations. One concerning, yes, U, that is the one you want to have. Another one that concerns B, that is an extra one, and you don't need it. And then you will have another equation for the dissipation variables. But the formula writing the Hamiltonian allows you to consider the one with the dissipation and always find a solution of it, no matter what U, B, P, X, Q, X is. Yeah, so it does not matter. The second thing is that once you have these things, yeah, by means of regularity, you get rid of Px and Qx and obtain a system of PDEs that depends only on U, B, and the first and the second order derivatives of U and B. And doing so, you can match quite easily the Hamiltonian so that you get your PDE. And you see, there are several keys to do so. They are very useful because there are a lot of things, there are a lot of methods. I think, I don't know if you wrote all the examples, but we have something like 20, yeah? 20 different, completely different examples. And we didn't write more because we didn't want to, yeah? We could have, but it had no sense. But this was very important to explain how these equations appear, because you want someone to use the method. You have to explain someone why it works and how it has to be applied. Otherwise, it looks like magic. Yeah.
Okay.
Okay. Thank you.
Okay. So okay, for now we continue. Just so okay, so partial, now we can consider damped sine-Gordon equation. I mean, it goes the same way. We have the partial differential equation. Now we are using the canonical to contact manifold with coordinates, and one may check that H looks like this. Okay, and it is the last one. So if we can also consider a partial differential equation that looks like this. And yet again, it is a yes, and yet again, it is a method with adapted exact to symplectic structure. So we are taking P0 equal to R8. We are taking the coordinates. We are constructing the differential form in a usual way. We are taking the yes, we are finding the k-symplectic 2 form, the k-contact, and then we can guess the Hamiltonian. And that's all. Thank you.
Thank you, Marcin. You know, it's the first time you give a talk about it, so we will work on it. Don't worry. It's something that one has to hear. We are here to learn. Okay, so is there any question, remark, comment? Well, I have a question. Do you remember that we have more applications, more things done?
We had more applications, right?
Yeah, I mean, more
yes,
applications,
I mean,
not
okay,
about
because
not examples. I mean, more techniques to study these examples. Do you remember?
maybe we had. I'm not sure now.
Symmetries, conservation
Yes, we
law.
had. Okay, yes, I skipped symmetries. It is true, right?
We could use symmetries, yeah, to obtain
Yes.
conservation for this model. Okay, okay. We will work on that. So, is there any other question? No. So, thank you, Marcin, for your talk. It's been a pleasure,
Thank
and
you.
we will see you all next week, I expect. Thank you very much.